Good morning, Nalod. Today we are starting our first session on theory of computation. This is the paper theory of computation, and in theory of computation, the first topic which we are going to cover is finite state automata. That means this is a tool. This is a tool which is used for accepting certain languages. Language means certain strings. For example, suppose that you have set of binary strings containing 101 as a substring. This is an example of a language. That means here that means the language accepted is any binary number or binary string which contains 101 as a substring. For example, 0101, 1101, 1010. These are all examples of such a substring. That means for accepting such restricted, that means this is the condition for that language. The language means set of strings as per that finite automaton, or this is the condition, and here we can generate a tool for accepting this, and that is finite state automaton. Here this is a finite state automaton which is accepting, or this is a finite state automaton which is used to add two numbers. For example, suppose that you have two numbers 10110, 01011. Suppose that these are the two numbers and you are starting from right, and initially the finite control is in state q0 and our inputs are 0 and 1. What will happen? Upon receiving 0 1, that means this is 0, the output is 0, and there is no carry. So this state q0 represents carry of q0 represents carry 0 and q1 represents carry 1. Okay, that means here initially in state q0 we don't have any carry, and if you are adding 0 and 1, that means upon reading 0 and 1 you will output 0, and control is turned back to q0. Now finite control is pointing to q0. That means after this step, initially this was in state q0 upon reading 0 1, this is the output produced is this one, and we are moving from right to left, and initially this was in state q0 upon reaching 0 1, it produced an output of 0. This is not output 0, this is actually, this is 1, and here also it is 1, and okay, it is producing an output of 1, and it is staying in the same state. Now what will happen? That means now finite control is pointing to the next bit after this, and now 1 and 1. What will happen in this state q0? If 1 and 1 happens, then the output is 0 and control is transferred to q1. That means control is transferred to q1. Now the finite control is having the state q1 and the output is 0. That means next it is moving to the next input symbol. Next, what is 1 0? But now the current state is q1. Now the current state is q1 means it is now the carry is 1. That's why it is in state q1. And in state q1, if 1 0, that means 1 0. Again, the output is 0 and control is given back to q1 itself. That means again q1. Okay. Now it is moving to the next pair of symbols 0 1, and in state q1 if 0 1 happens, 0 1 is the next input q1, then the output is 0, output is 0, and control is given back to q1. That means again the next state is q1, and now q1 is reading 1 0. q1 is reading 1 0. What will happen? Output is 0, output is 0, and a carry is generated, and the input is exhausted, and the carry is, that means that is not in our scope, that carry is carry forwarded, and this is the result. Actually 1 and 0, 1 plus 1 0, 1 plus 1 0, 1 plus 1 0, no, okay, this is the output. Okay, that means this is a finite automaton which is used as an output device. In the case of Moore and Mealy machine, finite state automata with the output, you will study this. Anyway, a finite automaton is having an input which is printed on a tape, This is a tape, and the left end of this is fixed, and the to the right end is not fixed. That means left end of this is fixed, and to the right it is not fixed. And here you have a finite control. Here you have a finite control, and the finite control is having a head, and that is pointing to the first cell. And it is, that means this is in state. That means initially that will be the start state. Initially the finite controller will be in the start state, and after reading a symbol it will switch to a new state or something like that. That we'll discuss later. Anyway, here the input is printed on the tape. That means here actually we are processing this from right to left. Actually we have, this is like this, and 0 1 is printed here, 1 1 is printed here, 1 0 is printed here, 0 1 0 1 and 1 0. That means here this may be the dollar, the right hand marker, and here this is the input, and the input is printed on this tape, and here initially it is pointing to the first cell, and the start state, in this case the start state is q0. See, when this finite control is in state q0 and q0 upon receiving 0 1, what will happen? As I told you, here we are moving from right to left. Actually here this is printed in reverse order here. That means we are moving from, that is actually 1 0 1 1 0, 1 0 1 1 0 is printed from 1 0 1 1 0. That means if you are adding, you are moving from right to left. Okay, you are moving from right to left, and here in this case these are the, that means after reading each symbol, here you have a pair of symbols. Okay, in this case after reading each symbol it will switch to a new state, and the next input, after reading the next input it will switch to a new state, and the next state depends on the current state and the current input symbol. That means current state is q0, and if it is reading 0 1 it will move to a new state, or it will switch to a new state, and that next state depends on the current state and the current input. For example, if it is in state q0 and if it is receiving on 1, it will switch to q1. If it is in state q1 and if the next input is 1 0, it is staying in the same state. That means the next input is dependent on the current the state depends on the current state and the current input symbol. Okay. Now a finite state automaton has a finite control. A finite control is in a state. Always it is in a state, and initially that will be in the start state, and initially the input is printed on the tape and the finite control has a tape head and it is reading the contents of the tape. This is a logical machine. There is we don't have any physical machines something like that. These are all logical things, and here we have a logical tape, and here you have a finite control. That finite control has here that will be in some state. That means after reading the current input, this will switch states, and the next state of this finite control depends on the current state, and the current input symbol. That means a finite automaton can be represented as a finite automaton can be represented as M is equal to Q sigma delta Q0 F. Okay, that means Q sigma delta Q0 F. That means Q is the set of states. Sigma is the input alphabet. Delta is the transition function. Q0 is the start state. F is set of final states. Okay. That means M is equal to Q sigma delta Q0 F. Q is a set of states. Sigma is the input alphabet. Delta is a transition function. Q0 is the start state, and F is a set of final states. We are extending our delta to delta cap. That means here delta is a transition from Q cross sigma to Q means, for example, in this case, delta of Q0 upon receiving 1 is equal to Q0, and delta of Q0 upon receiving 0, this is what Q1. And now we are extending, that means delta is the input to delta is state and one input symbol, current state and current input symbol. And now we are extending, or we have a new notation which is delta cap, and in this delta cap you can have Q0 upon receiving 100. What will happen? Q0 upon receiving 100, that is equal to Q2. This is Q2. Delta cap of Q0 upon receiving 100, this is Q2. That means multiple symbols you are going to provide here. That is why here we have sigma star means, here star means 0 or more symbols. Sigma, this star means 0 or more symbols from sigma. That means here Q cross sigma star means for every input symbol or for every state you are going to process the sigma star means it's a string derived from that sigma, and that is pointing to a new state. That means Q1 upon receiving delta cap of Q1 upon receiving say 00, what will happen? Q1 on receiving 00, that is also Q2, and likewise that is delta cap. Now delta cap is defined like this. Suppose that X is an element of sigma star means X is a string, X is a valid string, and A is a valid input, say single input symbol. A is an element of sigma. That means what is the difference between sigma and sigma star? Sigma means it is a single input symbol, and sigma star means it's a string derived from that sigma. And Q is the set of states. Now we are going to define delta cap as delta cap of Q comma xi. That means, suppose that you are going to have this xi. This 10 you are going to take x and 0 as a. So Q0 Xi is equal to, or as per our definition, delta cap of Q0 comma Xa is equal to, what is that? Delta cap of Q0 X, delta cap of what? Qx. That means Q0. Then what is x? 10 comma 0. Okay. What is delta cap of Q0 on 0? Delta cap of Q0 10 is Q1. That means this is delta of delta cap of Q0 on 0 is Q1, comma 0 is delta cap of Q0 100 means delta cap of Q1 comma 00. That is not the same. Delta cap of, what is delta cap of Q0 on 0? Q0 10 is Q1. Q1 comma 0, which is equal to, what is delta of Q1 0? Q1 0 is Q2. That is the definition of this. Delta cap of QA is equal to delta of QA. That means delta cap of a single, if the input is a single element string, or if the length of the input string is 1, then that is same. This is an example of a finite automaton which is accepting the set of binary strings which is ending with 00. That means any string, any binary string which is ending with 00 will be accepted. That means, for example, the language is defined as binary strings which is ending with 00. That means, for example, 100, 0100, 1100, etc., etc., 000. These are all coming under this language. That means, say any, you can test this with any number of, for example, suppose that you have a string, say 1100, 100. Suppose that your input is like this. Initially, the finite control will be in state Q0, and say using this figure, we can see that Q0 upon receiving 1, what will happen? It is staying in the same state. Q0 upon receiving this one, it is staying in the same state Q0, and it is advancing to the next input symbol. Now Q0 upon receiving 1, what will happen? It is staying in the same state, and Q0, next input is pointing to the next input symbol. Now Q0 is reading 0. Q0 upon receiving 0, what will happen? It is moving to switching to state Q1, and input pointer is pointing to the next input symbol. Input pointer is pointing to the next input symbol. Q1 upon receiving 0, what will happen? Q1 upon receiving 0, what will happen? It reaches Q2. It reaches Q2. That means now the new state is Q2, and the input is pointing to the next input symbol. That means Q2 upon receiving 1, what will happen? Q2 upon receiving 1, it is switching back to state Q0, and it is advancing to the next input symbol. Then Q0 upon receiving 0, what will happen? It is switching to Q1, and Q1 on accepting next 0. Q1 on accepting 0, what will happen? It is switching to state Q2, and that means after consuming all the input symbols, after processing all the input symbol, now this is finite control. This is finite control. Finite control of the finite automaton reaches Q2, and this double circle nodes represent a final state. Now, after processing this symbol, or after processing the input string, the finite control reaches one of the final states. Here, this is a final state, and final state is represented by a double circle, and That means this is a binary string, or that is a language accepted by, or that is a valid string according to this finite automata. That means that is a string in this language. That means our language contains 1100 100, and now we can test this using some other examples. Anyway, if it is a finite automaton which is accepting all binary strings which are ending with 00, then if you process this using this finite automaton, you can see that if a string is ending with 00, definitely the finite control reaches Q2 after processing all the inputs. Okay, so if you have, say, suppose that 1 also is added here, what will happen? That means this is not a valid string according to this. Then Q2 upon reading 1, what will happen? Q2 upon reading 1, it reaches Q0. That means after processing this, the finite control is in state Q0, which is not a valid string. Q0 is not a final state, so this is not a valid string. That is, any language is accepted by a finite automaton if after processing the input, if the finite control reaches one of the final states. Now, using this, we can define M is a phi tuple Q sigma delta Q0 F, where Q is the set of states. Here we have three states, Q0, Q1 and Q2. Q0, Q1, Q2. Okay, Q is the set of states. Now, sigma is the input alphabet, means in the input you are permitting only binary or bits. That means in this string we have only binary numbers. That means only zeros and ones are permitted. Sigma. Then delta is the transition function. Delta is the transition function, and that function is represented like this. That is Q0, Q1, Q2, and upon 0, 1. That means here this is like this. Q0 upon receiving 0, what will happen? It is switching to Q1. Q1 on receiving 1, what will happen? It is staying in the same state Q0. And Q1 on receiving 0, it is switching to Q2. And Q1 on receiving 1, it is switching back to Q0. And Q2 on 0, what will happen? Q2 on 0, it is staying in the same state. And Q2 on 1, what will happen? Q2 on 1, it is coming back to Q0. And in this arrow to one of the nodes represent, that is a start state. And this is the transition function delta. That means Q is the set of states, sigma is the input alphabet, delta is the transition function, and the start state is represented by an arrow. That means Q0 is the start state, and F is set of final states here, but we don't have a set, we have a single state. Can have more than one final state. Here in this case we have only one state, and F is the set of one or more final states. So this is a finite automaton which is accepting all binary strings ending with 00, and that is pictorially represented as a transition diagram like this. And in this transition diagram, an arrow which is floating on the left side, that means this is pointing to the start state, and final states are represented by double circle nodes. And we have the set of states Q, then sigma is the input alphabet, that means a set of permissible symbols in the input string, then delta is the transition function, Q0 the start state, and F is the set of final states. And this is for a finite state automaton is a language acceptor. It can be used as a language acceptor. That means if you are defining a language, and if suppose that if initially q0 w, that means delta of q0w, that means if your w is a string, and if this q0 on processing the input symbol w in one or more states, if it reaches one of the final states, that means delta of q0w, that means if you have an input string say 1100, that means this w stands for 1100, that means delta of q0 upon receiving 1100, if it reaches in one or more, that means this is in one or more steps, this is the meaning of one or more steps. If it reaches q2, suppose that if it reaches q2, that means this can be accepted, that means starting from the start state, that means the finite control is initially in the start state, and starting from there, if you are processing the input and after considering all the input symbols of the input string, if it reaches one of the final states, if the finite control reaches one of the final states, that means that language can be accepted, and this can be used as a language acceptor. And the most important application of finite state automata is it is used in the lexical analysis phase of the compiler. Lexical analysis phase of the compiler. Lexical analysis phase means you know what is a compiler, and it's a high level language program which is converting a high level language to machine language. So it's not a high level language program, it's a program which is converting your high level language program to its equivalent machine language program. And for that there are different phases like lexical analysis, syntax analysis, semantic analysis, code generation, etc., etc. And the first phase we are analyzing the input, and in that case we are splitting this your program into a number of tokens, and for that you are using this finite state automata. For example, in C language, the a valid variable name, the rule is valid variable name, valid variable name in C language. What is a valid variable name? There are two conditions. First character should be either an alphabet or underscore. That means a valid variable name in C language, a valid variable name in C language is the first character should be either an alphabet or underscore, and subsequent characters are either alpha numeric or underscore. That means here the first character should be either an alphabet or underscore. That means capital A to Z and small a to Z are permitted as the first letter, and afterwards you can have small capital A to Z, small a to Z, underscore, and 0 to 9. That means star means after the first character should be either capital A to Z or small to A to Z, or underscore also is there, underscore, and afterwards you can have any letter or digit or underscore can be there. That's a valid variable name in C language. So for generating this also we are using finite state. This is an example of a finite automaton which is accepting the set of all binary strings ending with 101. That means all binary strings which are ending with 101 is accepted. That means here, see, listen here. Here you have 1101. What will happen? That means starting from Q0 101. That means it has reached Q3. That means that can be accepted. What about 110 That means it will reach only Q1. That means for the next zero, what will happen? 110 1110 111 For the next zero, it reaches here only. That means for the next one, it reaches the final side. That means this will accept. This is an example of a finite state automaton which is accepting the set of binary strings which are ending with 101. And likewise, here you can, for example, suppose that if you want to generate, that means accept all binary numbers which are divisible by 3. This is another example. It will accept all binary strings which are ending with 3. That means here any number you take, either it will be divisible by 3 or it is generating a remainder of 1 or it is generating a remainder of 2. That means all those numbers, that means suppose these are the set of integers, then can partition this into 3. That means here remainder 0, remainder 1 and remainder 2. And when a number is divided by 3, then when you are dividing that by 3, if the remainder is 0, that number can be accepted. That means a number is either divisible by 0 or it is generating a remainder of 1 or it is generating a remainder of 2. That means for this, for tackling this question, or for here you have three states. Now I am going to have three states: Q0, Q1 and Q2. And this Q0 represents remainder 0, and Q1 represents remainder 1 and Q2 represents remainder 2. Okay, this is remainder 2. So starting from an empty string, an empty string means nothing divided by 3 is nothing. That means that will be accepted if an empty string will be accepted. And suppose that a 0 is coming. Initially, what will happen? Suppose that a 0 is coming. 0 is a binary number, and when it is divided by 3, again it is generating a remainder of 0. That means Q0 upon receiving 0, that is generating 0. That means initially suppose that you have a 0, then when that is divided by 3, again the remainder is 0. That is why you have 0. Suppose that initially you have 1. What will happen? Suppose that you have a 1. 1 means in binary it is 1, and when 1 is divided by 3, what is the remainder? The remainder will be 1. That means after this, if in the initial state, if a 1 is coming, what will happen? It will go to Q1. That means suppose that you have 0, 1. What will happen? 0, 1 is actually 1. When 1 is divided by 3, again it is generating remainder of 1. Suppose that you have 0, 0, 1. Then what is that? 0, 0, 1. 0, 0, 1 means it is 1. And 1 is generating 1 divided by 3 is generating a remainder of 1. And suppose that you have after this one, that means for this Q0 state, all the transitions are over. We have already defined the transitions for 0 and 1. Then what will happen? Here, the minimal length string that happens when suppose that you have reached Q1, that means you have received a 1. Can receive 0, 0, 0, 1, 0, 1 as well as 1. Simply take 1. And suppose that here the next input symbol is 1, 0. In binary, what is this 1, 0? That is 2. When 2 is divided by 3, what is the remainder? When 2 is divided by 3, what is the remainder? 2. That means here Q2 is the state. Q2 is the state uh, which is used for here Q0 stands for remainder 1, Q1 stands for remainder 2, and Q2 stands for remainder 2. That means after this one, if a 0 is coming, then overall it is 1, 0. 1, 0 means it is 2, and it is generating a remainder of 2. So we have an arrow to Q2 and it is demarcated as 0. Now what will happen if this is 1, 1? After the first 0, suppose that the next symbol is 1. Then what is this? Overall, it is 3. When 3 is divided by 3, what will happen? It is number 0. Or then 3 is divided by 3. When 3 is divided by 3, it is generating a remainder of 0. That means if the after this one, again the next input is 1. 1, 1 is generating a remainder of 0. And as it is generating remainder 0, that is represented by Q0, and we have to put an arrow from Q1 to Q0, which is demarcated as 1. Okay. Then Q0 to Q1 and Q1 to Q2. Now you have to define this. You have to mark the transitions for Q2. That means here the minimal length string which happens when you have reached Q2 is 1, 0. 1, 0. On 1, 0 it reaches here. Suppose that after this a 0 is coming. What is 1, 0, 0? That is 4. When 4 is divided by 3, what will happen? What is the remainder? 1. Here remainder 1 means that is represented by state Q1, and so we have an arrow from Q2 to Q1 and label it as 0. Now what will happen after 1, 0? Suppose that it is 1, 0, 1. 1, 0, 1, what will happen? What is 1, 0, 1? In binary it is 5. When 5 is divided by 3, remainder is 2. 5 is divided by 3, the remainder is 2. And here we are going to have an arrow 1. Okay. So this is to accept all binary strings which are divisible by 3. Here a remainder 0. That means if after processing a number, if the finite control reaches Q0, that means that can be accepted. Why? Q0 represents remainder 0. Q0 represents remainder 0. So you have to mark this as a final state. See example 1001. 1001. This is actually 9. 1001. What will happen? From the start state 1001. That means that can be accepted. That means 9 is divided by 3. Now 1100. That means 8 plus 4, that is 12. It is divided by 3. What will happen? 1100. 1100. Okay. That means all binary strings or all binary numbers which are divisible by 3 can be accepted by this finite automaton. This also is an example of a finite state automaton. A finite state automaton is actually a language accepted. That means if you have a finite automaton, then the set of languages that is accepted in the finite automaton is said to be regular. That means language accepted by a finite automaton is called a regular set. And or if you can generate a language which is accepted by a finite automaton, then we call it as a regular set. Okay. Here, LFM is the language accepted by a finite automaton, that is defined as language accepted by m is equal to x. X is a string such that x is an element of sigma star, means it is a string derived from sigma, where delta cap of q0x is a set of final state, means delta cap of q01 processing this x, if the finite control reaches one of the final state, that can be accepted. That's all. With this we have completed the finite state automaton, deterministic finite state automaton. In the next class, we will discuss non-deterministic finite automaton. Thank you.